Hi, it's Mr. Anderson, and today I'm going to take you on a tour of the periodic table. A book that I've been reading, I'm not quite done, but it's really fascinating, is called The Disappearing Spoon. It's written by this guy over here. His name is Sam Keen. If you want more information, you can go to samkeen.com. It's neat. It's got a lot of trivia on the periodic table. But it's essentially about the history of the periodic table. In other words, it's not the science, which I'm going to talk about today. It's more about the people who discovered the elements. It goes all the way from the Manhattan Project to Mr. Bunsen, the inventor of the Bunsen burner, and Mr. Lewis, famous for Lewis dot diagrams. So it's a fascinating read. And it's getting at the history behind this, which is the periodic table. Periodic table, we're going to come back to this in just a second, and we'll review some of the things from this podcast. The thing you may be puzzled about is what's up with the name of the title, The Disappearing Spoon. Disappearing Spoon is actually written about this element. It's called gallium. It's a poor metal. And the neat thing about gallium is that it has a really low melting point. And so if you mix your tea with the spoon made of gallium, so let's take a look at this video over here on the side. The minute it goes in the tea, you can see that it starts to turn into a liquid and then kind of melt away. Thus, the disappearing spoon. The problem with this, I was like you are saying, well, let me Google it. Let me buy one of these spoons. It seems cool. It's also highly radioactive, and so it may not only be a disappearing spoon, but it may be a disappearing hand if you deal with gallium too much. So let's get to the periodic table. So here's our periodic table. Periodic table, first of all, the vertical columns are going to be called groups. And so this would be 1 and 2 and 3. And it goes all the way over here to number 18, which is on the side. And the periods are going to go down the side. So this would be 1, 2, 3, 4, 5, 6, 7. And so we're going to see these periodic properties. In other words, as we go and look period to period to period to period, you'll find that there are similar characteristics. Let's go through it then. And I'm going to try to use different colors and highlight each of the different areas. So let's start with the first one. First one are going to be these metals. These metals are called the alkali metals, and it goes all the way from lithium at the top to cesium at the bottom. So these are called alkali metals. Alkali metals all have one valence electron. That means that they're highly reactive. And so in this picture down here, we've got lithium, sodium, all the way through cesium. If you want to have fun on YouTube, just look at alkali metals, and you'll see people thrown into water, and you get these huge explosions. And that's because of their valence electrons. Next to them are called the alkaline earth metals. And so let me advance our picture. So these are the alkaline earth metals. It goes all the way at the top with beryllium, all the way down to the bottom at radium. So this is alkaline. These all have 2 valence electrons, and so they're reactive as well. They tend to form oxides with oxygen, magnesium, calcium. All of these are important in living things. And they tend to be fairly stable. In other words, we can find them on our planet in a raw form. Next up, we've got the halogens. Halogens are going to be over here on this side. So this would be a halogen right here. Fluorine, chlorine, bromine, iodine, astatine. These all have 7 valence electrons, so that means they would love to get one more electron. So they're not super stable. Chlorine, pictured here in this block, is in a liquid form. It normally occurs as a gaseous form. It's a nasty gas. It was used as a poison during World War I. And these are the halogens right here, highly reactive. Right next to them, however, are the most unreactive of the elements that we have, and these are going to be called the noble gases. So helium, neon, argon, krypton, xenon, and radon. All of these have 8 valence electrons, and these are going to be called the noble gases. Really stable. They've got complete outer energy levels or valence shells, and so they're really, really happy. Unlike their halogen neighbors, which are right next to them. Okay, cool thing about them, if you look down here at this picture, you put any of the noble gases in a tube, run electricity through it, they're going to fluoresce as electrons kind of move to higher energy levels and then fall back down. So if you look at neon lights or lasers, are all made up of these noble gases. And if you ever have heard of inert gases are gases that don't react with anything. We use those in like MIG welding, be an application of that. Okay, next are the schnapps. Schnapps are a way that I like to remember the nonmetals. And so I'm going to circle these. So here's carbon. Then I'm going to go way over here and circle hydrogen. And then we're going to do nitrogen and oxygen and phosphorus and sulfur and selenium. So these are all called the nonmetals. The reason I wrote down schnapps is that these are all things that are vital inside living material. So carbon is what we're made up of. Nitrogen makes our amino acids. Oxygen is used to get energy out of our food. We use phosphorus in our DNA, sulfur in our proteins, and even selenium, which is not part of schnapps. We need micro amounts of that. And it's been linked to deficiencies in selenium can actually perhaps cause cancer. Okay, next one then are going to be the transition metals. And so if we were to circle those on here, transition metals are going to be all these down here. These are the transition metals. Transition metals have weird numbers of electrons. In other words, the ones that they're showing outside are variable. And so they all look the same, but they all have different characteristics. And so these are called the transition metals. Example would be gold. And so gold is going to be right here as a transition metal. And here's a block. This is the largest block ever of gold. I think it's 250 kilograms, so like 600-pound bar of gold. Neat things again, that verticality, silver is right above that, copper is right above that. They have similar valence electrons, and so these are all going to be similar. Next group then on the periodic table is going to be the poor metals. And so if we go to where those poor metals are, poor metals, let me find a good color. Poor metals are going to be, let's go right here and here. And here. These are going to be the poor metals in here. And so metals are going to be over in this group. This is gallium right here. This is a picture of gallium that was that disappearing spoon, remember, that melted away right at the beginning. These are going to be somewhat good conductors, but not as good as the true metals that we find over here in the transition metals. Next group then are going to be the metalloids, and so a good color might be red if I could find that. There we go. So the metalloids are going to be here. So that's boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. These are all going to be the metalloids. And these are all semiconductors, and what that means is that they conduct electricity, but they don't fully conduct electricity. I've got a block of one of them. This is actually a log or a large amount of silicon, and so this is a silicon crystal. What they do is they grow it into these great cylinders, and then they slice it off, and then they can stamp silicon chips out of it. So it feels a little bit lighter than it would if this was just a true metal like iron, for example. And if we run electricity through it, we can kind of control the amount of electricity that we run through that because it's a metalloid or a semiconductor. And then the last thing I put on here was uranium. There's a general trend that as we go farther and farther and farther down the periodic table, our size is going to get larger and larger and larger. And so when we get down to things like uranium, these are actually uranium cubes that were used in the Manhattan Project. Atoms are going to get larger and larger and larger. So when we go down to the bottom, this is uranium. Most uranium is in the form of uranium-238. That means it has 92 protons and tons of neutrons. And so the farther we go down the periodic table, things tend to get radioactive. In other words, parts of them tend to decay or to fall apart. One other interesting part here, this is the lanthanides and the actinides. The way a periodic table really should be organized is that these two rows here at the bottom should actually be inserted here. And the reason that most periodic tables don't show it that way is it would make our periodic table incredibly long, and so it really wouldn't display well on a poster.